In 10th grade, I took a class called AP Human Geography, where we learned about the different trends that led to the development of human civilization. The most important one of these is farming. And as human civilization has progressed throughout the years, we have developed new and innovative ways to produce food to feed the burgeoning US population and throughout the world. The most influential and one of the most impactful advancements that has been made since then has been the development of nitrate and phosphorus-based fertilizers, which have been employed throughout the US and the world. One of the main issues facing our farming community today in a state like Minnesota, which has a very prevalent farming community in the South, is the problem of nitrate runoff, where large amounts of water runs off fertilizers into local water systems, which can cause nitrate pollution, causing all sorts of harmful effects to the local environment. We are seeing the same trend in Asia, where large amounts of nitrate fertilizers are being washed into these very fertile river regions in China and India. And unfortunately, government regulation has largely failed to catch up with this problem. According to the United Nations Environmental Program and an expert named Tariq Aziz from Pakistan, nitrate pollution has been exponentially increasing since the introduction of these technologies towards these regions in the 1960s and 70s. The main problem being faced is that, according to China's Ministry of Water Resources, over 80% of all river basins in China are unsafe for drinkage by humans and are incredibly dangerous to local wildlife. The same problem exists in the United States, although to a significantly lesser extent because of government regulation. This made me ask my question, but before we get to that, let's talk about eutrophication and the process that I was examining throughout my study. Eutrophication is a system that rapidly depletes the dissolved oxygen within a local water system by depositing large amounts of nitrate-based fertilizers and other nutrients which feed the reproduction of blue-green algae. These reproduction and subsequent decomposition of the blue-green algae means that large amounts of oxygen are depleted, meaning that fish, plants aren't able to gain access to oxygen and die off as a result. This problem is made even worse because of the fact that blue-green algae also produce cyanotoxins, which can exhibit harmful effects of their own if humans or other wildlife are exposed for long amounts of time. So this brings me to my question today. Which is more harmful to zebrafish, cyanotoxins or eutrophication? The existing literature and research is pretty conclusive that cyanotoxins are incredibly dangerous towards zebrafish, both in their adult and their embryonic stage. The first piece of literature I examined was from the Chinese Academy of Sciences, which studied the effects of Microcystis aeruginosa as well as osculatoria on zebrafish embryos. The study concluded that zebrafish that were exposed to Microcystis aeruginosa experienced significantly higher rates of problems such as edemas, acute problems like liver failure, and also death, brain damage, as well as damage to the gills, which are important because the main way in which blue-green algae affects these zebrafish is through the depletion of oxygen. In this experiment, the zebrafish embryos were exposed between 2 and 96 hours post-fertilization. And it was revealed that at the end of the study, that zebrafish embryos exposed to osculatoria, a filamentous kind of zebrafish, experienced significantly lower levels of mutations than those exposed to Microcystis aeruginosa. That link between the filamentous cyanobacteria and the non-filamentous cyanobacteria will be important later on. The second piece of literature I examined was from the Pontifical University in Brazil, which studied the effects of Microcystis aeruginosa on adult zebrafish, which is more applicable to my study. This quantified the physiological and behavioral effects of zebrafish exposure towards Microcystis aeruginosa, and the resultant decreased travel by 66%, the time spent at the bottom of tanks by 93%, as well as resulted in acute damage to the liver, gills, and brain, and other long-term effects towards zebrafish. The conclusions we can draw from the literature that exists today is that cyanotoxins created by blue-green algae can cause serious physiological problems for zebrafish, like those I previously mentioned. There is also a possible link between the less severe filamentous cyanobacteria and the non-filamentous cyanobacteria, which cause lower deformities in those zebrafish. Finally, the current literature doesn't examine if eutrophication is more of a problem than cyanotoxin exposure, and that's where my study comes in, where I wanted to analyze the difference between cyanotoxin exposure and eutrophication results. And my hypothesis is as follows. While cyanotoxins may cause long-term issues for zebrafish, the lack of oxygen is more of a concern in the short term. which essentially goes to show that governments should possibly be trying to target eutrophication instead of targeting cyanotoxins with their government regulation and other sorts of actions. That eutrophication will cause higher mortality than cyanotoxin exposure within the immediate term. The methodology is that 2 different zebrafish were placed in 3 different tanks, surrounded by nostoc or filamentous cyanobacteria at varying amounts. I had one tank, Tank C, which is a control tank, Tank A, and Tank B, which were filled with varying amounts of cyanobacteria. 2 trials were conducted, one without and one with the presence of air stones, to examine if that and the addition of oxygen were to impact the mortality of the zebrafish. Trials ran for around 1.5 weeks each, and dissolved oxygen measurements were taken using a combination of the Winkler method as well as with an oxygen probe. This is the lab setup here, where we have Tank A on the left and Tank B on the right. Tank A had significantly higher amounts of cyanobacteria, and Tank B had lower levels, but still a significant amount of cyanobacteria, which negatively impacted the amount of dissolved oxygen within both tanks. Right here we have a picture of zebrafish, and this one right there, that is significantly darker than all the surrounding ones, is a fish that actually survived the study that I will go into later. But as you can see, there is significant changes to the coloration of its skin. You have red lines appearing all across the zebrafish. Furthermore, it exhibited behavioral changes towards the tail end of the study, like swimming at the bottom of the tanks, just like previous studies predicted they would. The data and lab results for trial 1 were pretty conclusive. Dissolved oxygen were in each of the measurements were taken in each of the tanks. Tank A had around 3 parts per million, and Tank B had around 7 parts per million, measured on April 1st. To contextualize, normal water contains around over 10 parts per million. Tank C did not receive any measurements, as because I alluded to previously, that was the control tank where no blue-green algae existed. On April 5th, 2 zebrafish were added to each of the tanks, and on April 7th, all but one of the fish in the tanks died. One Tank B survived, which is the tank that I showed in the previous picture. Moving on to trial 2, in order to confirm that the previous deaths were due to eutrophication and not cyanotoxin exposure, I added in air stones to make sure that the fish were exposed to plentiful levels of oxygen. Measurements that were taken afterwards showed that oxygen levels had increased substantially to around 10 parts per million. After the air stones were added, the fish survived until April 28th. We are going from the fish surviving just over 2 days without air stones to that one fish which had been exposed with in the previous trial, surviving just over almost 2 weeks with the air stones being added, showing that oxygen levels were a significant help and increased the life expectancy from the previous trial. The conclusion from my study is that eutrophication poses a significantly higher risk to aquatic life than exposure to cyanotoxins. So, as with any study, there were some significant limitations and reflections that I have made once the study was ended. And these are the 3 main ones. The first is the scale. The small sample size in trial 2 could have significantly impacted the accuracy of my results. It could have happened that that one zebrafish that survived simply had stronger protections against cyanobacteria than other ones. If I were to expand the scale of the experiment, the likelihood that abnormal variations within zebrafish or abnormalities in the study pool could have negatively affected the results. The likelihood that would have happened would have significantly decreased. Observations also were a significant restraint. Due to the aggressive time frame, I didn't have time to test for other significant observations like pH levels, which could have negatively impacted the zebrafish. It's likely that the pH levels could have sharply decreased, which could have led to the deaths of the zebrafish instead of eutrophication. However, if we would have taken pH tests during the first trial, if those were normal, we could almost guarantee that eutrophication and the decreased levels of oxygen were the cause of death for those zebrafish. Finally was the time frame. Starting my experiment later in the year forced me to take time-saving measures, like moving away from the Winkler method, which was a time-constraining and time-consuming method of finding the dissolved oxygen levels, moving towards an oxygen probe. But with the study concluded, we can arrive at the conclusion that my hypothesis was indeed correct. However, if I were to do it again, some significant changes like expanding the sample size, as well as making more qualitative and quantitative observations would have been needed in order to verify my hypothesis and conclusion that presented itself at the end of the study. Thank you.
All right, thank you. How did your review of the methods used by scholars in the field inform your selection of a research method that aligned with your question?
So when I was looking at those two studies I mentioned previously, those scientists surrounded their zebrafish in a very level amounts of cyanobacteria. On top of this, in order to control the amounts of oxygen, some of the studies added different air stones or other methods to control or to at least monitor the levels of dissolved oxygen. In order to study the effects of eutrophication specifically, I decided to go along with what they were doing somewhat by adding air stones to ensure that I could manage and tinker with the amount of oxygen, so that was what was causing the deaths in the previous trials.
Okay, thank you. How does your new understanding address a gap in the scholarly conversation?
So most of the zebrafish research that I found that was testing with blue-green algae were studying primarily the physiological effects of cyanotoxin exposure on the zebrafish instead of whether or not that was being compared with eutrophication, for example. I didn't really find much research to indicate that one was more harmful than the other or how that was being addressed in the field. So in order to make up for this gap, I decided to study eutrophication and how that specifically would harm the zebrafish at varying levels of oxygen decreasing in the different water systems. So because of that gap that existed, I decided to go towards examining eutrophication, the depletion of oxygen, instead of examining physical changes or mutations that would have arisen from cyanotoxin exposure.
Okay, thank you. How did you handle the uncertainty of the research process?
So starting at the very beginning of the year, there was a lot of uncertainty surrounding what kind of question I would use. I knew I wanted to test zebrafish and blue-green algae, but unfortunately trying to pick a perfect question that satisfied my desire to pick a question that I actually cared about and something that I was really interested in meant that I had to constantly delay or change my experiment or study the minor details, meaning that the time frame was negatively impacted. I could definitely say that I could have handled that better, being more aggressive and more decisive in dealing with the uncertainty at the beginning of the year. But once the study got rolling, I was able to quickly counteract some of the lost time and pursue my experiment aggressively and in an efficient manner.
Okay, thank you.